Nobody took the idea of warp drive seriously until 1994, when a theoretical physicist, Miguel Alcubierre, proposed a method that could, within the realm of known physics, warp space to travel faster than light. Alcubierre's discovery set theoretical physicists abuzz. Could FTL travel be possible? Even NASA got interested. Alpha Centauri is about 4.37 light-years away. Let's make it 4 for simplicity, so it takes a beam of light 4 years to get there from Earth. Unless I can go faster than light, a round trip is at least 8 years. And that's going at the speed of light, not counting the time it takes to accelerate to that speed and slow down at Alpha Centauri, our fastest probe ever. NASA's Parker Solar Probe, launched in 2018, will only achieve a max velocity of 200 kilometers per second. The speed of light is 1,500 times faster. Getting a probe even near that speed would be impressive, but if I can go faster than light, maybe a lot faster, I could cut that round trip time down to months or even less. Such a possibility had already been entertained within the physics community decades before, with research into what are commonly called wormholes. Like Alcubierre's idea, wormholes are a distortion of space, but instead of being a bubble that a ship carries with it, they are passages through space that can take you from one point to another in far shorter time than going through normal space, like a high-speed railway. Wormholes had been discovered in 1916, only 1 year after Einstein published his theory of gravity called general relativity. Compared to warp drive theory, they are ancient, but hardly less exotic. Wormholes also feature in Star Trek, but except for the alien-constructed one in DS9, they are regarded as unstable. In the more near-future sci-fi franchise, Stargate, however, they are the de rigueur way to travel to other stars and galaxies. For those of us who envision a future humanity traveling to the stars at FTL speeds, a burning question is which is more likely to become a reality: warp drive like Alcubierre drives or Stargates? Let's look at the differences. The Alcubierre drive warps space so that anything inside its bubble will be accelerated not by a means of propulsion, but by compressing space itself. This is like a mini form of how the universe expands, but in reverse and local to the bubble. Because it is distorting space and not traveling through space, it can go faster than light. Over the last 26 years, a great number of criticisms have been published about Alcubierre's idea. It will need a universe of energy. It will generate intense radiation, destroying both what is inside the warp bubble and what's in front of it. It will make it impossible to control because one cannot send messages from the back of the ship to the front without exceeding the speed of light. It will need a bubble that is so thin it would be outside of known physics. Still, all these seemed like engineering problems, or at least potentially solvable. Surely a clever engineer in the future could design ways around them, make a more clever bubble that needs less energy. Perhaps some protection could be developed for the radiation, or it could be deflected or sucked away somehow. And who is to say we can't make a super thin bubble? Still, maybe wormholes are the easier path to the stars. A wormhole is like a tunnel, but with one more dimension than usual. It consists of 2 ball-shaped openings separated in space. Unlike depictions on Stargate and Star Trek, the opening is not a 2-dimensional disk, but a ball you can enter from any direction. The 2 balls are connected by an opening called a throat, which is the surface of a sphere that exists outside normal space. This sphere is analogous to a circular joint between 2 pipes, but in one more dimension. As you enter one ball, you don't pass through an ordinary tunnel. Rather, you enter a distorted space where instead of passing through the ball and out the other side, the direction you are traveling along is bent outside of normal space. The bending causes you to pass through the throat and out the other ball, and you spend the whole time on the wall like an ant. You never see the walls of the tunnel because the walls are 3-dimensional, crawling inside an hourglass. You can even send a signal in a straight line from inside and it will circle around and come back to you. It's hard to visualize, which is probably why science fiction rarely gets it right. Early wormhole solutions to Einstein's equations, including the one that Einstein himself discovered in the 1930s, were impossible to travel through because the wormhole's throat was pinched off faster than even light could travel through. It wasn't till 1973 that Homer Ellis discovered a traversable wormhole, one that you could actually travel through in Einstein's equations. Like warp drive, building a wormhole would also turn out to be a challenge. To create such a large distortion in space-time, you would need to connect 2 black holes, one for each end. To do that, you need to merge the two black hole singularities while keeping the black holes themselves separate. Then you need to blow up the merged singularity from a point into a spherical throat for an opening. Quantum theory might help with that through entanglement, where objects can be connected together at a distance. Others have suggested naturally occurring quantum wormholes might appear in the vacuum of space in a subatomic realm called the quantum foam and be encouraged to enlarge to allow something to pass through. So far, none of these mechanisms have been shown to be physically possible at the size needed for anything classical to pass through, like a probe. Wormholes turn out to be a tough one. A third method that I've yet to see in science fiction is the Krasnikov tube. This idea was proposed in 1995 as an alternative to the Alcubierre drive. In it, a ship would distort space as it goes at sublight speed from one star to another. Instead of making the journey shorter like a wormhole, the tube is a time machine. Let's see how it works. To go 4 light years at that speed is 4.04 years for us, but for the probe it is only 7 months. The reason has to do with relativity and the twins paradox. You see this principle in the Ender series of books by Orson Scott Card. Ender and his sister travel so much that they live thousands of years Earth time. The Krasnikov tube is designed to distort time behind the probe so that people on Earth don't have to wait as long for the probe's return. Once the probe reaches its destination and is ready to return, it enters the tube and travels back the same way it came. The only difference is that, as it travels, time runs in reverse. This has the effect of allowing it to arrive shortly after it left. Most FTL mechanisms, including wormholes, Krasnikov tubes, and Alcubierre's warp drive, require matter that has negative mass or some source of negative energy. For wormholes, negative energy creates a repulsive effect that keeps the throat of the wormhole from collapsing on itself long enough for something traveling at or below light speed to traverse it. In the Alcubierre mechanism, the exotic matter is required to get the balanced front and back distortions that the warp bubble requires. The Krasnikov tube needs it to reverse the flow of time, so where do we find negative energy? Classical physics has no notion of negative energy, since in that theory you can't have less than nothing, but in quantum physics there is no such thing as nothing. One example of negative energy is the Casimir effect. Quantum theory predicts that in the empty vacuum of space, you have waves and particles appearing and vanishing all the time. These random vacuum fluctuations are effectively at zero energy, sometimes called zero-point energy. The Casimir effect occurs when you bring two parallel plates close together in a vacuum. In between the plates, longer wavelength phenomena can't appear because they are interrupted. Less waves means less energy. So the energy in between the plates is lower than the energy of pure vacuum, negative energy. The Casimir effect violates an energy condition called the weak energy condition, which is the most intuitive measure of the energy. We can measure the plates being forced together even in a vacuum with no other forces present, which implies the condition is violated in between the plates. Theoretical physicists such as Nobel laureate Kip Thorne and others point to the Casimir effect as one potential source of negative energy that could drive an FTL engine or hold open a wormhole. If the plates could be brought close enough together without touching, they could create massive amounts of negative energy. In 1992, Stephen Hawking conjectured that anything that can go back in time or send messages back in time requires, on average, negative energy, and being the party pooper that he was, said that this is impossible. He called this the Chronology Protection Conjecture, a way the universe protects the timeline. Since all known FTL mechanisms, including wormholes, warp drives, and Krasnikov tubes, can potentially be turned into time machines, Hawking's conjecture rules them out. A conjecture, however, is just an educated guess. Others argued that quantum physics could easily have negative energy and pointed to the Casimir effect. Then in 2007, Hawking's conjecture won the battle. Two researchers, Graham and Olam, building on Hawking's work, demonstrated that while quantum physics, including the Casimir effect, violates some energy conditions, others are absolute. In particular, the Achronal average null energy condition, or AANEC, may be the ultimate cosmic traffic cop, making all FTL travel from warp drives to wormholes impossible. Graham and Olam showed that quantum physics never violates the AANEC. Any time machine, they further showed, has to violate this condition. But what does the AANEC actually mean? The Achronal average null energy condition refers to the average energy over certain kinds of paths through space and time. Null paths, also called light-like paths in general relativity, are the paths of light speed. Achronal paths are when you can't travel between 2 points in space and time at sublight speeds. Achronal means not time-like. If you send out a beam of light in a straight line, it is an achronal null path because nobody can catch up to it. If you bend the light, however, so that you can catch it by taking a shorter path, then its path is not achronal but still null. You would have to travel at or above the speed of light to catch an achronal null path, which hints at why these are so important for FTL travel. They are, unfortunately, exactly the kinds of paths one needs to have negative energy in order to travel faster than light or back in time in any way. And as far as physics is concerned, the AANEC is the law. It puts the kibosh on both stargates and star drives. While the discovery has not propagated much outside theoretical physics, and some remain skeptical that we fully understand quantum physics well enough without a full theory of quantum gravity, it has brought a lot of the excitement over FTL travel to a halt in the physics community. Some major players dismiss FTL entirely because we now have to modify known physics, either relativity or the standard model, to justify it. Of course, that does not dismiss warp drives and stargates completely. While Alcubierre drives and wormholes cannot make us go faster than light, we can use them to travel slower than light. This means that we could potentially still use negative energy sources like the Casimir effect to warp space in order to propel starships at subluminal speeds. In 2018, Maldacena showed it is theoretically possible without violating the AANEC to connect two charged black holes into a very long wormhole. What's possible for wormholes is probably possible for the Alcubierre drive. Why would you want to do that? One of the advantages might be to help prevent the crushing acceleration that traveling near the speed of light would require. Since the Alcubierre drive allows objects within its bubble to be in freefall, it could be a sort of inertial damper, allowing far more rapid acceleration than ordinary rockets would allow. It would be like a ship falling towards its destination, rather than a rocket pushing the ship ahead of it. The time it takes to accelerate to a significant fraction of the speed of light is considerable. If we ever want to send humans to the stars, it will be important to protect them from acceleration. In Arthur C. Clarke's Rama books, he recognized the problem and suggested using foam packing. This is why, despite the impossibility of FTL travel, NASA is still justified in studying it. We can't say that we won't be traveling with warp drive in the future. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.